here's the alarm route with the measure values. So we can start at a starting point of 0 and ending point of 1.7 miles. In between, we'll have at each mile distance from the beginning, we can have each range, the jurisdictions and speed limits. It'll be at the exact mile distance, if you will. So there are so many rules that essentially the guidebook called them business rules, but I'm not gonna go through all of them. Some core business rules that mentioned is, for example, one is to provide the information via web services using an online portal supported by the United States Department of Transportation. The second one would be the proposed NRBM data structure must support facility inventory using linear referencing, provide basic topology, be vendor independent, so there's no bias for vendors, provide the means for multiple modes of travel to be included, be constructible over time in a modular fashion. The next rule is the data editing and data usage environments must be separate. The next one is the enterprise LRS should be extensible to include all entities in the facility inventory. An LRS must provide 4 essential functions: to locate, to position, to place, and to transform. And then organizational issues at the end, as mentioned, such as creating match points and assigning globally unique route identifiers. So each state will have to be the arbiter of boundary issues at the location of match points within the territorial jurisdiction. And then FHWA will be of the state boundary match points. So to create a geographic location of the county parish level, the state duty will assign an agency identifier to each data supplier, including itself. So the data source will assign an internally unique identifier for each data object it supplies. So as far as business rules, there are 49 business rules that are mentioned in this guidebook. I'm sorry, 59. And these are just a few to mention here that there are business rules placed in the guidebook. So the core dataset components provide the national coverage. A proposed set of optional components accommodate roadway elements with independent geometry and additional business data. Example, let's see if I have that. Along a segment, we can also have information in each link that will contain business data, not just only the speed limit, but we can have roadway cross sections, like we mentioned earlier. We can have noise walls, we can have guardrails. So from this mile distance to this mile distance, we have a guardrail or a noise wall, or the counts of bridges and tunnels, and I'll touch on that with my example now that I'm showing. Payment sections, projects, curves, radius of curves, vertical, horizontal curves, super elevation, and so on and so forth. So it's a great guidebook that I believe it gains momentum. It already gained momentum, and it will be very good to see where we go with this. FHWA, they clearly have a um, they have a clear vision, and they're pushing for this to become a reality. There are projects that already some universities such as ASU and Dr. Zhu and his team, the PhD students, are working on this. And I just want to show one small example that I work with Dr. Zhu, just to stress the importance and how this can help if we follow this Aegist guidelines, and what the group here at ASU has done for um, for this particular matter, if you will. So this is a class example that I picked. San Joaquin County in California. There's a project that I'm working at my work that essentially I will need to figure out routes to transport big TBM or tunnel boring Stockton to 4 different locations, which are the shaft sites called. And in order to do that, I will need to create, have the map of the roadways throughout this county that will help me, that I will need to analyze and figure out how I can get these huge machines from the port of Stockton to each of the main shafts. So data collection, what we see here in this picture, is from OpenStreetMap. So the steps that I performed are opening OpenStreetMaps. It's free and it's available for everyone. In OpenStreetMaps, I I type the county, the San Joaquin County, and I found out what is the um, essentially what is the code for that county. I took that code and I placed it into the OSM to GMNS package. This is what Dr. Zhu's team at ASU has uh, come up with. This is a Python code that is created to help convert the uh, essentially the map that I from the previous slide to be converted in, and to extract the links and the nodes from each of the rows. So now this is the second step where we install the OSM to a GMNS package. You can see this is the county's map. Previously worked there is a city of Tempe here in Arizona and Manhattan with their codes. This is the code from the San Joaquin County, and this is the code here where Python it's extracting it from the um, dot open source map. They're creating a network model from OpenStreetMap exports. This is how the model is created. My video is covering partially of this, of the map, but this is essentially the San Joaquin map with the main interstates, state routes, and essentially interstates and state routes. Um, Point of interest, I went too fast. The point of interest for this particular map, I had some issues. I was getting errors, but I've done this. I performed this on the city of Gilbert, and the point of interest were there. And essentially, at the end, when you get all of these, you export the transportation network model It's a CSV file format that you can then import into GIS or QGIS for presentation. So this is kind of like a, in a way, what the Aegist is talking in their guidebook. It's a little more simple way, and it's very helpful to see that there's a progress um, in that sphere, if you will, and eager to see what's the next step and what's coming. So with this, wrap up my presentation. There are so many open questions, and there is so much work to be done yet. But this is definitely a beginning of new era, if you will, in the infrastructure industry. So thank you, and